In this lecture we shall present the notion of image of a subset of the domain of a mapping and state two useful properties regarding this notion. Suppose that F is a mapping from A to B, and suppose that A' is a subset of the domain of F. Then sometimes we're interested in the subset of the codomain of F, consisting of all those elements in the codomain for which there exists an element in the set A' that maps to it. We refer to this subset as the image of A' under F and denote it by F applied to A'. More precisely, we define F of A' as the set of all y in B for which there exists an x in A' such that the f of x equals y. Let's consider a couple of examples. First, consider the mapping f from integers to integers defined for all x by f of x is equal to x squared minus 1. The image under f of the set consisting of the integers 0 and 2 can be found by following the arrows starting in the x-axis at 0 and at 2. It is the set consisting of the integers minus 1 and 3. The image under f of the empty set is the empty set, and it always is, irrespective of the definition of the mapping. Further note that the image under f of the set of all integers is the set of all endpoints on the y-axis of arrows starting in integer points on the x-axis. It is, hence, the set of all integers y for which there exists an integer x such that y equals x squared minus 1. For a last example, let's change the domain and the codomain of the mapping under consideration from integers to real numbers. Then the image under f of the set of real numbers is the half-open interval from minus 1 to infinity. That is, the set of all real numbers y greater or equal minus 1. We shall now present two properties of the notion of image. First, if we have an element of the set A', then clearly this element maps to an element in the image of A' under F. And there we have our first property of image. Whenever x is in A', then we may conclude that f of x is in the image of A' under F. You may wonder whether the converse is also true. So does it follow from f of x is an element of the image of A' under F that x is an element of A'? Well, the picture already suggests that this is not the case. But pictures may be deceptive, so you should always work out a concrete counterexample. To this end, consider again the mapping f from integers to integers defined for all x by f of x is x squared minus 1. Now take x to be minus 2, and A' to be the set consisting of the integers 0, 1 and 2. Then f of x equals 3, and the image under f of the set consisting of 0, 1 and 2 is the set consisting of minus 1, 0 and 3. Note that 3 is in this latter set. So the f of minus 2 is in the image under f of the set consisting of 0, 1 and 2. But x, which equals minus 2, is clearly not an element of the set consisting of 0, 1 and 2, which is A'. Thereby, we have refuted the statement at the top. Nevertheless, we do know something about A' if we have an element that is in its image under f. Namely, if we have an element in the image under f of A', then there must exist some element in A' that maps to it. Recall the formal definition of the image of A' under f. It gives rise to another useful property of image. Namely, the statement that y is in the image of A' under f is logically equivalent to the statement that there exists an x in A' such that f of x equals y. This property can be used in two directions. From y in f of A', we may conclude the existence of some element x in A', such that f of x equals y. But also, conversely, if there exists an x in A', such that f of x equals y, then we may conclude that y is in the image of A' under f. The picture you see here is one to remember because it visualizes all our general statements about image. But perhaps more importantly, you should remember the two properties of image that we have presented, because those you will use to construct proofs. This concludes our discussion of the notion of image. In the next lecture, we will construct an example proof using the two properties of image that we have presented in this lecture.